It's not raw touch.
Look at how big they are.
It rubs.
Anyways, no one gonna tell me how big they are.
No, it's not. It's literally the main thing.
Find a clear picture.
Okay, let me go over the calendar here. So we have one more new topic to go over. This is directional bearings. It's really just more of a kind of a half section. So I think we're going to be able to spend time kind of starting our application. So I think the most challenging part of the unit are just the word problems, which we're going to be able to spend quite a few days on. So if we can get an early start on it today, I think that would be good. And then hope to get back your quizzes by Monday. Okay. And then we can go over that as well. We'll have just additional days to do test review, and our test will just be next Thursday, right before our President's Day weekend starts.
When do you think the quizzes will be?
I hope to grade it by the weekend and return it back to you on Monday. Okay. Okay, so let's go to page 21. Okay, so typically, whenever we talk about angle measure, we always start on the positive x-axis and then we move in a counterclockwise direction. But anytime we see the word bearing, bearing directions are angles where we're measuring clockwise and we're starting from the north. So basically, we're going to treat north as 0 degrees and we're going to measure out in the clockwise manner. Okay. I'm going to kind of go through the full process here, and then there's a bit of a shortcut for bearings, and but I don't want to talk about that until we kind of understand the process here. Okay, so it says if I want to find a bearing of 220 degrees, essentially I'm just starting at this is my quote unquote 0 degrees. And I know that every quadrant is going to be 90 degrees, right? So 90, 180, 270, 360. But if it's a bearing of 220, that means I got to travel 90 degrees, then another 90 degrees, and then a little bit more, right? So 220 degrees starting here in the clockwise would land me in the third quadrant. Okay. So now this would be where the angle is. But then to convert to a measurement in standard position, we have to kind of figure out where this is in relation in terms of, between 0 and 360, counting from 0. So what we can do is, well, we know that this is really 270, right? First up, we know that this one between this degree measure between 220 and 180, we know this difference is just going to be 50 degrees, right? There's a 50-degree difference here. And if we know that it is 50 degrees from the y-axis on heading south, then we know that's really 270 minus 50. Let me see here. I'm sorry, not 50. This is 270 between 180 and 220, it's just going to be 40, right? Sorry, 40. And if we know that it is in the third quadrant, 40 degrees from 270, we can do 270 minus 40, which is going to be 230. Okay, or we can measure from this. Either way, we just have to kind of keep track of the fact that, you know, we're measuring it from this north degree, but then we have to account for the fact that we're trying to convert it back to be in terms of standard position. Okay, so direction, sketch the angle given in bearings, then determine the angle measure in standard position that is coterminal with the given angle. Okay, so bearing of 160. So right now, this is the degree measures are given like as if we are measuring from the north, right? So 160, we know 160 means that we're going to have to travel 90 degrees and a little bit more, right? So 160 is going to be here. Now we know that 160 is 70 degrees from the x-axis. So how do we convert this to something that is in the fourth quadrant between 270 and 360?
360 minus.
Yeah, 360 minus 70 will tell us where, you know, using this as a reference angle, we can subtract from 360 to get to a measure that is fourth quadrant, right? So 360 minus 70 will give us 290 degrees. Okay, bearing of 335. So that means we're just going to 90, 180, 270, 335. We know it's going to be somewhere in this fourth quadrant. Oh, sorry, somewhere in the second quadrant here. And then 335 minus 270. Right, so that's 65. So we know it's going to be 65 degrees from the negative x-axis. And now we can kind of erase everything else and just think of this as reference angle, right? So reference angle, we know to get to the second quadrant, we can do 180 minus 65. Okay, is that making sense? So if you can figure out what that reference angle is, then you can just erase all the numbers and just imagine, okay, I just need to find the closest x-axis and either add or subtract my reference angle to get to the quadrant that I want to be in. Okay, can you guys try number 3? After we get through 3 and 4, there's a bit of a shortcut that can just allow us to get to the standard position a lot faster. But the reason I want to go through this is I want you to understand where these values are coming from, how to draw in a degree measure from a bearing position. Okay, where's 212 going to end up? Third quadrant, right? So this is 90 plus 90 to 180, and it's going to be between 180 and 270. Okay, so 212 minus 180, or you can do 212 involving 270 as well. Either way, just have to make sure that whatever measure you find, you just are going to involve the standard position. So let's say I wanted to go after this here, 270 minus 212. So if I know that it is 58 degrees past the negative x-axis. I can use that to help me find my true third quadrant measure. Okay, any questions here? Okay, try number 4. Okay, 241. So from here, 90, 180, 241 is going to be less than 270 here. So if I can find that reference angle, I can now ignore these numbers and just add it on to 180 to get something that lands in the third quadrant. Okay, so before I talk about the shortcut, does this make sense in terms of bearings and just counting from the north and going clockwise? Okay. So if you go to the very last page of your packet, there's a bit of a summary sheet here. And I'm gonna write this on the this previous page as well. But it says here, true bearing is measured from the north with positive angles opening clockwise. True bearing measurement is just 450 degrees minus, I'm sorry, this is not the one I want to use. It's this second one here. So standard position, if I'm given bearing, I can just do 450 minus the true bearing measurement, and that will give me something in standard position. So if I can just always subtract from 450, I'm able to get that measure without having to draw everything out and subtract and go through all that process. The reason why 450 is involved is because we're counting 0 from the 90 degree. So everything gets shifted. So instead of subtracting from 360, we're subtracting from 450 because 450 is just 360 plus 90. So everything is kind of shifted 90 degrees. So if we kind of take that into account, we can always figure out what the standard position is by just subtracting from 450. So let's just practice that shortcut process and see if all of our answers match up like we would expect them to. Okay, so the formula that we're going to be using here with the shortcut is standard position. Any standard position that I'm looking for is just going to be 450 degrees minus whatever bearing. They call this true bearing because on the next page, we're going to be talking about bearing that is starting from a different location. So 450 minus the bearing will give us the same thing as if we were to draw everything out. Okay, so let's just practice that here. If I do 450 minus 160, because this is bearing, I'll get the same answer, right? 290 degrees. Okay. Bearing of 335. If I want to quickly get to the standard position, 450 minus 335. I'll get 115. Okay. Bearing of 212 degrees. If I want to quickly get into standard position, subtract from 450. If I'm given a bearing of 241, subtract from 450. Okay. Any questions there? Okay. Now we can only do the shortcut if they give us something that is like a true bearing, meaning that the next page we're going to be talking about bearing that's starting at a different location. If that's the case, we're really going to have to kind of draw it out. But if it just says bearing of a degree measure or true bearing of a degree measure, we can always use this formula to just quickly get that number into a degree measure that's more suitable for everything else that we're doing, all the formulas that we have. Okay, any questions on this first page? Good. All right, page 22. Okay, so now we have something called directional bearing, where the directions are angles given as starting direction, either north or south. So we're always going to be starting either north or south. And then an acute angle of rotation measured towards the second direction, either east or west. So now we can basically start anywhere and move in either direction. But they're going to be providing more information to tell us how to move, which direction to move, and how much to move. So for instance, if it says bearing of north 20 degrees east, what we're going to do is we're going to start north, because that's what they're going to ask us is to start here. And we're going to move 20 degrees towards the east. So that means we're going to be moving from north towards the east 20 degrees. So we're going to go clockwise. And then once we have this, then we can decide what that standard position is. We know that this is 20 degrees off of 90. So 90 minus 20 will be equal to 70. Okay. All right. Second example, if I have bearing of south 41 degree east, that means I'm going to start south. This is my quote unquote 0. And I'm moving towards the east 41 degrees. So I'm going to move 41 degrees east, which is going to land me in the fourth quadrant. And if I know that I'm in the fourth quadrant, I know that this is just 41 degrees away from 270. So 270 plus 41 will give me a standard position that is consistent with what we expect from a fourth quadrant degree measure. Okay, does that make sense? So the first direction is going to tell you where to start, and the second direction is going to tell you whether to go clockwise or counterclockwise. Okay, good. All right, let's look at some examples. Okay, bearing of north 60 degree west. So that means we're starting here and we're going to move 60 degrees towards the west. Okay, 60 degrees towards the west. So how can I find that? How can I find the true standard degree measure that's in the second quadrant? Yeah, so either you find this degree measure to be 30 and do 180 minus 30, or because they're starting from the north, I think it's easier to just do 90 plus 60. I know that's not normally what we do, right? Normally, we like to think in terms of reference angle and everything with the x-axis, but in this special case, because we're using the number that's off of what we expect, I think it's easier to just start wherever what we know to be the standard position and then add from 90. I know that's not normally what we do, but for bearings, we're going to try to make it, well, we're going to make an exception. I think it's a little bit easier this way. Okay, let me do one more with you, and then have you guys try 7 and 8. Okay, so number 6, south. That means we're starting south, and we're going to move 35 degrees towards the east. So we're starting south, and we're going to move 35 degrees towards the east. So that means that's going to land us in the 4th quadrant. We want a degree measure that's consistent in the 4th quadrant. But for now, we can kind of draw this 35 degrees to the east. So that's the same thing as 35 plus what? Just 270. Yeah. Okay. Any questions so far? Does that make sense? Okay, try 7. Okay, which quadrant are we going to end up in? Yep, 1st quadrant, right? So you're starting at direction being north, and then you're moving towards the east. So how can we find the true degree measure here? Good. 90 minus 72, because we want an angle measure between 0 and 90, right? We're expecting 1st quadrant degree measure here. Okay. Any questions with 7? Try number 8. Right, which quadrant will we end up in? 3rd quadrant, yeah. So starting south, you want to move towards the west, 11 degrees. Right, how can we quickly get to that 3rd quadrant standard degree measurement? Yep, 270. We want something between 180 and 270. So if I subtract 11, from 270, I can get there. Okay, so anytime we're given the bearing measurement, we always want to get it into standard position, because standard position is a true degree measure that will work with the formulas that we've been accustomed to using. Okay, so we're going to start and see how much we can get into our word problems. Okay. Any questions so far? Okay, we'll just try to get through. We probably won't get through the entire first page, but we'll just see if we can just take it slow and kind of go through it one by one here. Okay, does anybody still need this page? Okay, at the top of the page, I'm just going to write down the formulas that that we've been using so far. We kind of just have easy reference to them. We know magnitude. That's gonna come up a lot. Magnitude is just once we have it in component form, we just imagine taking finding the hypotenuse, right? Square root of a squared plus b squared. We know that if we're looking for direction, we always have to involve inverse tangent. And then if it's in the second, third, or fourth quadrant, we may have to involve 180 and 360, but at least this will give us our reference angle. Okay. We also have component form, which we will use a lot, which is the directional or the magnitude cosine theta will be the horizontal component. Hypotenuse or magnitude sine theta give us our vertical component. And then another popular one that we're going to see a lot is angle between vectors, which is the dot product of two vectors, or cosine theta equals the dot product divided by the product of their magnitudes. So multiplied together, right? We use that on our quiz. Okay, let's read example 1. Train A and B depart from the same station. The path that train A takes can be represented by vector and component forms. That's nice. The component forms are already given to us. If the path that train B takes can be represented as 55.4, find the angle between the two vectors. Okay, so really it's a word problem, but really they're just giving us the two vectors and we just have to find that angle. So we can just take this and dump it, put it into our formula for angle between two vectors. Okay, so I'll treat this like, I'll call this vector A, I'll call this vector B, and I'm just going to adapt this formula. Okay, let's find the dot product. So 33 times 54. Or sorry, 33 times 55. Magnitude. So magnitude of vector A, we can just do Pythagorean theorem. Times magnitude of vector B. Okay, so see if we can get all that into the calculator here. To gain the most accuracy, if we can enter all this in within one statement. Make sure you're in degree mode. 15.823 is what I have. Okay, so really what you've been able to do on the quiz yesterday is just present it in a word problem format. Okay, example 2. Airplane is flying at a direction of 115 degrees at 530 miles per hour. Find the component form of the velocity of the plane. So here, they're giving us something. If they say it's direction of 115 degrees and there's no bearing and there's no direction, then let's just treat it like standard position. Okay, so this is nothing tricky here. We just take this at face value. That's our theta. Okay. Okay, this is our magnitude. So it's as simple as putting it into component form. Magnitude, in this case, is represented by speed. So this is the component form of the velocity. So if we were to take the fact that the plane is flying in this direction at this mile per hour, if we were to take that vector and break it down into its horizontal and vertical component, we can say that, okay, this is 223 mile per hour moving left with a vertical component of 480 mile per hour moving to the north. Okay. The nice thing of getting everything into component form is later on, when there's different vectors, different forces acting on the same object, if we can break everything down in terms of a horizontal and vertical component, we can add everything up very nicely. We can get, what is the true results of those two forces acting on the same object. Okay, everybody good with number 2? Okay, a captain sails a boat for 200 kilometers at a bearing of 150 degrees. So this is true bearing here, but this is not standard position, right? How do we get this measure into standard position? Yeah, it's always going to be 450. Unless they give you something like this, right? If they give you like north, 60 east, then we got to just draw it out, okay? But if it's just bearing, we can just quickly get to the degree that we want just by involving 450. So this is the standard position degree that we really want. Okay, from here it's easy. Now it just feels like number 2. Okay. Magnitude, cosine of theta magnitude sine of theta. Okay, example 4. Jordan is riding the bus to school. The bus travels north for 4.5 miles, east for 2 miles, and then north 60-degree east for 1.5 miles. Find the component form of the resultants. Okay. So what we're going to do is we're going to create 3 separate vectors, each vector having its own direction, and then if we add up all those components, then we can get that component form of the resultant. Okay, so the first is it travels north, right? So I'll just call this vector 1. Travels north means that I'm not having any left or right movement, so it's just going to be 0, 4.5. Vector 2, I'm traveling east. So how do I represent east in component form? Positive 2 and then 0. Okay. Now vector 3, we need to do some work here because let's draw this out because it's not very apparent what this is. We need to get this into component form. So to the side here, that means I'm starting north and I'm moving 60 degrees to the east, which is really what degree in standard form, standard position? Yeah, this is 90 minus 60, which is 30. So to the side here, we're just going to take this information and create the component form just for this path, this third path of this of this bus. So vector 3 is going to be 1.5, right? Magnitude cosine 30. And then 1.5 sine 30. So it took a little bit more work because it wasn't a nice, easy, straight up and down, left and right. We had to kind of get this diagonal vector into its horizontal and vertical parts. But now that we have our vector 3, we can find the resultant vector just by adding all the pieces together. So all the x's get added together, all the y's get added together. My resultant vector is just going to be vector 1 plus vector 2 plus vector 3. Okay, so I add up all the horizontal components, 0 plus 2 plus 1.299, which gives us 4.5 plus 0 plus 0.75. Okay, everything makes sense? Okay, we'll stop early today. We already got a little bit ahead, so we'll finish up the rest of the worksheet tomorrow, and then we kind of have an idea what to expect with these word problems heading into next week. Okay, let me come around and check your pages. So I want to check 21, 22, and 23.